Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this section, section 4, we're going to learn about the directing effects for aromatic systems. Okay, so this is aromatic systems part 2. We've done all the work leading up to this very last section before the finale. Okay, so what's going to happen here, let me explain to you what's going to happen. You're going to learn about how each group would direct another group coming into benzene. So for example, if you have a bromobenzene, where would the next group coming in go? That's what we're going to talk about now. And it's either going to be ortho, meta, or para locations around the benzene. After this video, we're going to do some problems to make sure that we understand the basics. And then the final section, section 5, is where we put everything together and we get to the heart and soul of this chapter. This is section 5, where we learn about how to take a benzene and make all these complicated products, and based on the rules that we're building up now through the past 4 sections. Okay? All right, so let's get started. The first thing I want to point out, here's the chart that you just have to know. And again, I showed it to you in the previous video. On the top are our activators. Now I want you to recognize that all activators are ortho-para directors. What that means is that if you have a benzene and the benzene has on it already Z, and Z is an activator, so it could be any one of these right here, then the next thing that comes in is going to go either ortho, the second position to Z, or para, the 4th position. So that's the first thing. All activators are ortho-para directors. Now, notice that halogens are unique. Halogens, they're deactivators, but they're ortho-para directing. And we'll see why in a moment. But that's very unique because besides halogens, all deactivators are meta directors. Okay, so all activators are ortho-para director. Halogens are ortho-para director, and all other deactivators are meta directors. And we're going to see why in just a moment. All right. Now, we're ready to do it now. Let me explain to you the philosophy. Okay. Now, benzene has something on it. It could be a halogen, it could be a Br, it could be a carbon, it could be an oxygen, it could be a carbonyl. And what benzene is smart enough to do, and it's actually more of electron density, but I like to give benzene credit like it's intelligent. But what benzene is smart enough to do is, based on the group that's already present, it will direct the next group where it best serves the benzene. And I'll show you what I mean. Let's take a look at right here, an ortho attack. So imagine that this right here is an activator. So it's an ortho-para director. So this could be an activator, or it could be a halogen, right? That's what we know. Now, if this is a halogen or an activator, right, that means that when the next group comes in, it's going to go ortho or para to it, and I'm going to put it ortho. So that means that I'm going to put it on the left or the right side of Z. Now, in this example, what I chose to do is to put it to the right side. So notice how E winds up over here. And notice that by doing that, this double bond winds up going over to E. Now that means that the positive is down below. Now what I want you to see is that if I do resonance from here, if I shift this double bond over and then I get positive over on the left, then I drop this down, I get positive up above. Notice something important, that when you direct ortho to whatever's already on benzene, that the carbon that holds this group becomes positive. That is the key. So benzene, knowing that this is an activating group or something that can help it, even halogen can help it, then it's going to make sure the positive carbon becomes the one that holds Z. Because now here's what can happen. If Z has a lone pair, so if Z, let's say this has a lone pair, it's like oxygen, for example, or halogen, then what this can do is it can drop down and give us a new resonance form. Not only is it new, but this is actually the best. This is the best form that you can get. Why? Because notice that you get an extra double bond. These all have two double bond, two double bond, two double. This one has three double bonds. So by directing something ortho, it is great if it's an activator or an atom like halogen because it gets an extra resonance form. But here's the thing, not all activators can do that. So the only one that gets the extra resonance form is if it has a lone pair, right? So imagine, for example, if I have, let's say, a double bond here, here, and here, and let's say a methyl. Well, when I use E plus, something comes in, I break the double bond. When the carbon, let's say it goes here, ortho, right? When this becomes positive, in this case, I didn't have to go around the ring because I did it in, I positioned the double bond in a way that's better than this one. See, here it's over here, so it's ortho to the Z, but it's not touching the double bond to the Z over here. It's just a question of switching the double bond. But when I do it this way, notice that the carbon that holds the Z group, that's it, it's tertiary. That's great, cation. But it doesn't have any more resonance because this methyl has no lone pair. You could do resonance in the ring, but you can't do it outside the ring. So this is an example of an ortho directing group, but it doesn't have an extra resonance form. What it does do is it gives a tertiary carbocation, right? Because it's methyl, so you get a high degree. So ortho directing, if the atom has a lone pair, you get an extra resonance form. But if it doesn't have a lone pair, it's still good because when the carbon becomes positive that holds the group, the ortho directing group, it's going to be a higher degree cation. Okay, that's it. That's the logic for ortho. Okay, so just keep in mind, I'm going to clean this up so that it's not so dirty when you, print this out. That's fine like that. Now, that only occurs if there's a lone pair. If there's a lone pair, then this happens. All right, so this is the best form on the right if you can do it, or this is the best if no lone pair. Why? Because then you get a higher degree carbocation. Notice that if this was a methyl, this is a tertiary cation. This is a secondary cation. This is a secondary cation. So this is the best if there is no lone pair. I hope that's clear. I think it is. Now you should be able to do this on your own. I type it out because it's a pain in the butt to keep writing this over and over again, and with my handwriting it's a mess. So that's why it's typed out. But you need to be able to do this yourself. All right. Now another thing I want to point out is that if the double bond is drawn out like this, like let's say like this or like this, these are the same thing. I want you to realize that these are not different. These are resonance forms. See, all we're doing is shifting. If this double bond shifts over here, and this shifts over there, and that shifts over there, then you get this on the right. So they're not different. So you could draw it either way. Now, usually if you have an ortho attachment, you want to put it where the double bond is already on the carbon that's directing ortho. So I would rather put something here because there's a double bond, but you don't have to. Like I showed you up in this example over here, we use the double bond here. It's not the one that's attached to the carbon with Z. It doesn't matter because it's all the same thing. It's all resonance. Okay, so just keep that in mind. But what's really important here, let me emphasize, is that when you have an activator or a halogen, then you want to direct ortho so that the carbon that holds the activator or halogen becomes positive. And for one of two reasons. A, it'll be a higher degree carbocation if it's like methyl or something, ethyl, methyl, and so on. Or you'll get an extra resonance form if it has a lone pair. Okay, that's why, by the way, halogens do this. Halogens are deactivators, but because they have a lone pair, they also direct ortho-para. Okay, even though they are deactivators. Okay, so that's a little bit special. Let's look at para. Para has a similar idea. Now, again, para occurs if you have an activator or a halogen, right? Or a halogen. Then you can get ortho and para. Well, para is across from the Z group. So imagine if this is an activator, then the next one in, or halogen, the next one in is going para. So I'm going to make sure that the carbon that's para gets the E. So I have to look, where's the double bond to that carbon? It's on the left. So I'm going to draw it out like that. And now notice that when you see the double bond, where you know you're going para, so this is the double bond I'm using, when I pull it out, then this becomes positive right there on the left because it lost the double bond, right? Okay, and then from here you have resonance. So this can go here, and then you get that positive above, and then from here you have two choices.